Yeah, thank you everyone. Yeah, thanks everyone for joining today's session. My talk today is going to focus on the aspect of algorithmic scalability of layer one blockchain protocols. Um, Broadly put, this is a topic of research that has been ongoing in my research group for some time. And the purpose of today's talk is to just sort of give you the big picture advances that have happened in the last maybe decade or so in this space. And I will focus mostly on the academic advances, less so on some of the innovations that are going on in the field outside of the academic literature. I may mention it briefly, but I will not give it the same level of center stage importance in this talk, since this is focused more on research and foundational ideas around that has been established in the peer-reviewed literature. Also, I'd like to mention that it'll be fun to have an interaction. So if you are interested in having a chat while I'm speaking, just feel free to chat on the chat window, or even unmute yourself and speak out your thoughts. Okay, so the story, of course, starts with this paper written by Satoshi Nakamoto, a person whose identity is yet to be traced in the real world, with this idea of Bitcoin, which is basically the definition of what a blockchain-like system would be. This was written in 2008, and of course, if you fast forward, even a decade later, there have been an explosion of cryptocurrencies or other blockchain-related designs that have come out, starting with the basic architecture that was provided by Bitcoin, the underlying technological base provided by Bitcoin. And so it's reasonable to ask, why is it an interesting problem to study for researchers and academics and even industry at the same time? And the reason is that blockchains provide you a new model of trust in some sense. And to argue that, you have to look at how people build trust outside of the blockchain world. So for example, many times you just do that on blind faith. You just trust certain things because you trust those things. Other times you do that because there is a reputation associated with the entity that you're interacting with. It's word of mouth, for example. Your friends and your neighbors have told you that this is a wonderful thing to do, and so you trust their idea and their opinions. In other cases, there may be good incentives for you to interact with the service, both financial and non-financial. And lastly, regulation, for example, is something that's prevalent in many industries, where there is rules and frameworks put in place to make sure that nothing unsafe or nothing seriously unsafe happens in those markets. And so there's oversight on the activities of all the actors in that ecosystem. So these are all ways by which we build trust in prior systems, right? In some sense, the idea that Bitcoin was proposing was interesting because it is actually offering you a new way of thinking about trust, right? So what it was saying is that if you have a laptop or a computer, at some point, you can plug into the system and you can verify everything that's happening on the system yourself, right? So anybody can audit what's going on, and the system will be available almost all the time. And we're going to guarantee the more the people connected to this network, the more will be the availability of this system, right? And so it's auditable, it's highly available. There is no single permissioned provider who's or a centralized coordinator that's going to be responsible for making sure that all of this works. It's going to be a large-scale community-oriented event, right? And when you start to think about why this is interesting or game-changing, is because there are many examples, but one to clearly look at is, how do we deal with digital currencies, right? So if you think about the problem of having a currency, really, let's distill down why a blockchain, or what is it that a blockchain really provides compared to any other sort of computing system before that, right? So if you think about it, let's say there are three players, right? Alice, Bob, and Mary. And let's say initially they own one digital coin each, right? What you could do is you could get these participants to transact. Even without a blockchain, they can transact, right? So for instance, Bob could pay $1 to Mary, and Alice could pay $1 to Mary, and this is fine, right? And both of these transactions can happen simultaneously, right? Because all three of these players have $1, and so if they want to transmit, Bob and Alice want to transmit $1 to Mary, there's absolutely no problem with doing that. Okay. Similarly, if Alice wants to pay Bob $1 and Bob wants to pay Mary $1, this is fine. Their balances are enough to do that, right? But if you think about the last two transactions where Alice is paying Bob and Alice is also paying Mary at the same time. Okay, so imagine these two transactions happening simultaneously, in one click, for example, happening simultaneously and are accepted by any payment system. Okay, that would be a problem because obviously Alice has a single dollar, and it's not possible for Alice, or should not be possible for Alice, to pay both Bob and Mary the same dollar. Okay, this is what's commonly known as a double spending problem. Okay, so let's think about what is this double spending and why exactly is it an interesting problem to look at. Okay, so if you step back a little bit and ask yourself, what is blockchain really doing for you more generally? What it's doing is you can think of it as the following problem. Okay, you have lots of these machines that are connected in a network. Okay, and these machines have the ability to process lots of transactions. These transactions could originate from any part of the world. So let's say there is some transaction 1 and some transaction 2. They're done on the opposite ends of the globe. Okay, one in, let's say, North America and one in Asia, right? And what you want is lots of these transactions are happening, and you want this machinery, so-called the blockchain, right, to be able to produce these things called blocks. Okay, these are basically time-ordered lists of transactions that the system has accepted to be valid. Okay, so in some sense, we call these as confirmed transaction blocks because each block consists of an ordered list of transactions that have been accepted by the payment system, and each block has there's a time sequence to each block, and therefore even the set of blocks are also ordered in time, right? So if you can do this, and if all of these computers can sort of agree that this is the order in which the transactions are confirmed, then this is exactly what we are trying to solve. Okay, the key challenge is to make sure that all of these machines in the network, okay, agree over what is the sequence of transactions that are accepted. Okay, so there are lots of transactions that are coming to the system, okay, in the sort of the input pool of the system. Over time, some of those transactions are going to get confirmed, and not only that, all the computers that have run this protocol will agree that here is a sequence in which we have accepted these transactions. Okay, so for example, if you look at these transactions, like Alice pays $1 to Bob and Alice pays $1 to Mary, you can get two different orderings here, right? Alice paying Bob first and then Alice paying Mary. This is one ordering that you could get within a block, for example. And the other ordering you could get is Alice to Mary and Alice to Bob. Okay, so both of these transaction sequences are valid. Okay, they are, both of these transaction sequences are valid in the sense that if Alice has enough balance, if she has $2, it's okay to execute both of these, and if she has a single dollar, then neither of these should really have been accepted. Okay. Actually, one of them should have been accepted, right? And so in carrying that thought forward, if you think about it, if I give you a full ordering of all the transactions, okay, first of all, two different orderings of the same transactions is not the same thing. We have to choose between one of them, and so all of these machines should agree on the same ordering. Okay, and secondly, the idea is that once you order these transactions, basically you don't have any double spending problems. Okay, why is that? The reason is because let's say Alice had a single dollar only. Okay, then the first transaction here, once we have agreed on these transactions, I would just pick the first transaction that has been accepted. So Alice will have transferred that dollar to Bob, and on the second transaction, you see on the left-hand side, the second transaction, Alice would have no longer any money to transfer to Mary. And so you can just literally forget about this transaction and just forget it, right? You can just step over the transaction and say, this is something, we don't care about this, okay? So what I'm trying to explain to you is that ordering transactions, okay, is sufficient to prevent double spending, okay? In fact, if you think about Bitcoin, it does not actually require to detect any double spends specifically. All it needs to do is order all the transactions that it receives. And then after that, all the wallet software can actually read that ordered list and pick the first valid transaction, the first valid spend of every coin. Okay, that would be sufficient. If there's any transaction that's trying to spend an already spent coin, such as the transaction 2 on the left block here, okay, you can just ignore that transaction and move down the list. Okay, so it turns out that if you were able to actually get agreement on the transactions that have been accepted by the system, it would be sufficient to avoid double spending, somewhat differently from what, slightly in a different way than what Bitcoin does. Okay, now, why are we interested in getting a total order, a complete ordering over accepted transactions? So it turns out that this idea is kind of rooted in something that's very well established in the distributed systems literature, in the academic literature on distributed systems, and this goes by the name of replicated state machines. Okay, so the idea is, and by the way, this is the basis for doing backups, doing snapshots, distributed lock systems, and so on. Lots of stuff that actually underpins cloud technologies today. Okay, so the way to think of this is that what we're trying to do is we're trying to determine for a replicated computing system, which has many, many, many nodes. Okay, we're trying to determine what is a sequence of states that these machines are going through. Okay, so think of this as follows. Imagine all of these machines that I've shown in blue here are running some program. Okay, we'll think of that program as a deterministic program. So it's not randomized. That means given the same input state, it's going to go to the same output state. Every time you run it from that initial state, it's going to produce as output the same output state, okay, because it's deterministic. Okay, and so what you're doing is, if you want to think about the execution of any such program, you can think about this set of machines as moving from one state to the next one. Okay, it's in initial state, let's say 0, and then by looking at a certain input or a certain input transaction, as it's called, it will move from state 0 to state 1. Then on reading transaction number 2, it will move from state 1 to state 2, and so on and so forth. Okay, so in effect, what this is telling you is that you can run pretty much any program of your choice, any state-oriented program you can run on a replicated state machine, as long as you are able to agree, okay, as long as you're able to agree on the sequence of sequence of state transitions, or the sequence of transactions that are seen as inputs by the whole system. Okay, why is that? You think about it as follows. Let's say I got 8 transactions all of a sudden as inputs to this system. Let us say these machines run some protocol. We'll call that as a consensus protocol. These machines ran some protocol, and as a result of it, they were able to agree on the following ordering of these transactions. Let's say T1 followed by T4, followed by T5, T8, T2, and so on and so forth. Okay, any ordering is fine as long as they agree. Now, if they all agree on this, this particular log of events, then basically each one of these machines can go at this first point, start from an initial state, apply the transition corresponding to T1, and move to the next state, and so on and so forth. They will simply move their local state from the initial state to the next one and to the next one, applying in sequence the transactions that are shown in this agreed order. Okay, and all the machines will do the same thing. And by sort of simple logic, you'll recognize that if all the machines started in the same state, and if they all apply these transitions in the same state, the program, the effective program they're executing, which is the same, okay, is going to move from the same set of states starting from the beginning. Okay, so they will all come to the same point after having executed, let's say, slot number 8. Okay, so that's the idea of using replicated state machines in distributed systems. Okay, so blockchains in particular are somewhat related to this concept. Okay, they are basically very large scale consensus protocols which allow lots of machines to agree on the sequence of transactions that they will process. And as a result of this idea of being able to move from one state to the other, they can actually execute programs. This is what enables general purpose computing on top of a blockchain infrastructure. Now, this was, of course, originally proposed in academia at various points, but this idea of smart contracts, which is embodied quite prominently in Ethereum, for example, it shows that basically you can do pretty general purpose computation using replicated state machines, which can be implemented by blockchains, for example. Okay, and lots of interesting things have happened. Millions of smart contracts have come about on the infrastructure that sits today on popular blockchains. Okay, so any questions about any of what I have talked? Okay, let me move forward. Okay, now let's talk a little bit about security. Okay, in this talk, I'm going to focus on sort of a notion of blockchain protocols that, first of all, correspond to permissionless blockchain systems. These are blockchain systems that are open for anyone to connect to. And in particular, I will focus a bit more on proof of work blockchains for this particular talk. Of course, many things that I mentioned here could very well be extended to proof of stake protocols and so on. And I'm happy to discuss that as we go on towards the end of the talk as well. Okay. The idea that underlies blockchains is that, first of all, it'll start with some genesis block. Okay, the first state that all the machines start with, all the nodes on a blockchain start with, is some pre-agreed, well-determined initial state called the genesis block. Okay. Now, the other three assumptions are pretty clear. First of all, anyone who is welcome to join the network. The machine, when it joins the network, does not need to have any pre-registered identity. You just have some IP address and you can just connect to the infrastructure. You never have to declare that I'm person X or organization Y and so on and so forth. Okay. There is some assumption about some fraction of the total computational power connected to this infrastructure. There's some assumption saying that at least some part of it, some fraction F of this computation power, is going to follow the protocol. Okay, so the fraction F that does not follow the protocol is considered to be malicious. We can assume that it does arbitrary stuff. It doesn't need to follow the Bitcoin protocol. It can do whatever it wants. And so we call this as an adversarial computational power in the network. Okay, and lastly, there is some assumption which we'll discuss a little bit more about, is that this network is able, it's connected in a way that it's able to transmit small blocks with some delay. Okay, for example, if you're sending a 1 megabyte block, it takes, let's say, 5 seconds to transmit it to everybody who's connected on the internet, on the blockchain infrastructure. Okay, so there's some sort of belief that networks will remain synchronous. Okay. Now, what you really want to do is two set of properties. Okay, these are called as actually three sets. The first is called safety. Safety says that once I've confirmed a block, then it cannot be changed. Okay, once a node has said that I agree to accepting this block, then basically it can't be undone. Okay, and secondly, safety also means agreement. That means if there are two honest players or n honest players on this network, and if one of them confirms a particular block, then the other participant should also confirm that block. Okay. Not only that, both of these participants should confirm these blocks in the same order. Okay. Another property that you would like to have is liveness. You want the system to be available, and so you would like that as long as there are honest people connected to the network, eventually, after some time elapses, honest blocks are being processed, new blocks are being mined, and those blocks are not malicious, right? Lastly, you want some sort of decentralization of fairness property. Okay, what that means is that the number of blocks that you're confirming per unit time is should be proportional to the total computation power that you have used. Okay, so let's say a particular members of a city decide to put together a giant cluster and connect it to the Bitcoin infrastructure. Then let's say they have 10% of the computational power of the network. Well, then 10% of the blocks, roughly on average, should be their blocks. Okay, that's kind of the fairness property that they want to achieve. Okay. Because there's a question saying, how do banking systems prevent double spending that is different from blockchain? One of the ways a bank system could prevent double spending, by the way, it is a challenge, by the way, if you don't know, there are incidents where double spends do happen in centralized networks. In fact, if you think about ATM machines distributed all across the world, let's say you use a ATM card on two different ATM machines geographically very far away from each other, and they both try to debit money. Okay, there is a small chance that both these transactions, which are effectively double spending, they're both trying to spend the same amount of balance, right? All the balance in the account. There's some chance that the server might accept this first. Okay, one ATM machine might accept this and dispense the cash, and the ATM machine on the other end might also accept it and dispense the cash. It's possible, and the reason is the ATM machine will read, oh, how much is your account balance? Let's say $100, and say, okay, I'll allow you to take the money out, and I'll debit it by 100. And the same operation is happening concurrently in the other side of the world, right? So both of these operations are happening simultaneously, and so you need to make sure that somehow the two discover each other in time, and one of them doesn't go through. So this problem exists on every distributed system. The way this happens in centralized systems is, first of all, you use very fast networks. So your hope is that these two concurrent transactions don't have a big window of overlap. And number two, actually, there's no sort of critical, there's no well accepted, there's actually very difficult to solve the problem. So what sometimes happens is you put limits on the amount that can be withdrawn, which means if double spends do happen in a centralized system, then at least they would get detected after the fact, and the damage would be limited. Okay, so this is sort of the way of dealing with this is to sort of, in some sense, be available, have liveness, allow the service to go through, but sacrifice safety. Okay, and if you sacrifice safety for some time, later on you can go and figure out, oh, there was these two transactions and two withdrawals happened simultaneously. You can take some retroactive actions associated with that. For example, contact your customer and find out what really happened, or deal with it in terms of insurance and so on and so forth. Okay. Yeah, but this is a very good question to ask. In fundamentally, the issue exists on every distributed system. Yeah. So the centralized players who are using large distributed systems, cloud systems, and so on and so forth, and even payment services, right? They always have to deal with this problem. Okay, let me move forward. All right, yeah. Okay, so let's take a look at how Bitcoin tries to deal with this, okay? And the answer is they're actually, Bitcoin system developed a new consensus protocol to do this. And it was surprisingly simple. And in fact, this has been consensus is a very, very famous problem in computer science and has been studied for 4 decades and more. And this was a very interesting solution to the problem. Okay, so let's take a look at this. Here is how it works. Miners, or these computers connected to the infrastructure, what they do is they keep a local copy of the entire blockchain. Okay. And what they do is to select which block or which set of transactions to accept at the present instance in time. What they do is everybody basically tries to solve a proof of work puzzle. Okay, this is how the Bitcoin or the Nakamoto consensus protocol works. Okay, and what is this proof of work puzzle? Think of this as trying to randomly guess an n-digit number. Okay, and the way this works is that if first of all, you have to do a lot of tries, okay, computational attempts in order to get that right number. If you do get it, however, then you basically have mined a block, okay. And what does that mean? What that means is that you get to choose some sequence of transactions that you like. You call that as a block, okay, a new block, okay. And then you're computing some sort of a cryptographic hash on top of it, which is like taking a random guess for a digit, okay. And if you manage to get a particular sequence of zeros at the beginning, okay, that means it's lesser than some 0000 followed by some other number, right? If you hit that little sweet spot, okay, then not only have you been lucky and your block is going to get confirmed, it also makes sure that you can present this hash that you've computed and tell people that, hey, you actually found the puzzle. Anybody can see this hash, can look at your the block that you're proposing, okay, look at the last block that they have locally, and together with this number s, this is a random number s, look at these parameters, run the hash once and check, your solution is correct, okay. The point here is finding a solution to this log puzzle is a lot harder than just checking whether the solution is correct, okay. Okay, so what happens is, now you might want to think about, this is fine, like what's so great about this, right? Like, I mean, if I have 10,000 machines, everybody's trying, there's a chance that somebody will get lucky at some point. And that's exactly right. Now, the thing is, the way you choose this parameter D, okay, the number of zeros that you want at the beginning, okay, the pattern of zeros that you want at the beginning, okay, you can set that in a way such that roughly you will make sure that 1 in every 10 minutes, for example, only one computer on this network will be able to find this, okay. Now, this guarantee is not saying that there will always be a single computer. All it's saying is that the chances that 2 or more than 2 machines simultaneously find the solution to this problem, that will be pretty low, okay. The chances will be very low. It's not 0, but it will be pretty low, okay. And so the way this protocol works is it keeps setting up this number D, so that depending on how many machines are connected right now, you can kind of guess how hard this puzzle should be, so that 1 out of all of this computing power is able to solve the solution, okay. Now, if this is good, because if there's one solver, if 1 every 10 minutes, okay, let's say on average, most often than not, if there's a single solution found in 10 minutes, the time taken to broadcast that solution is kind of small. It's a few seconds, okay. And once it's sent out to all the other machines, they can very quickly validate it, check it, okay. And if it is correct, they will simply accept that block and add it to their local copy. That's pretty much it, okay. Now, this is other interesting bit, which I should mention, and this was perhaps a very cool key innovation, and that's where the name chain comes in blockchain, okay. What Nakamura proposed is that here's what you should do. You look at your local copy of blocks that you've received, okay, and each block is extending a previous block through this hash, right? You see here that the last block hash and the new block hash are tied together cryptographically, right? And so this new block is extending the previous block, okay? What you do is, if you want to look at this entire chain of blocks, okay, you just pick the longest chain in your local copy, okay, and you accept the blocks on that chain, okay. Just remove the head of the chain, like let's say the 5 or 10 blocks at the beginning. You actually, in Bitcoin, it's supposed to be 6. Remove the first 6 blocks, the top 6 blocks. Confirm all the other blocks sitting on this longest chain, okay. Yeah. So here's another way to look at this from a bird's eye view. Imagine there are all of these computers sitting on this network, right? And they are all trying to solve this proof of work puzzle. Eventually, one of them gets lucky, right? Just somebody gets lucky at some point. Let's say P3 got lucky at some point. And that's when they have found a solution. They have a block and they have a hash corresponding to that block. And they're basically going to send it on this peer-to-peer network, right? They're just going to send all this data to everybody, and everybody floods it to everybody else, right? And finally, every node can locally verify whether the solution is correct. And if so, we call this P3 as the new block founder. If the solution is valid, we are just going to accept that solution, and everybody will extend their chain in the same way. Okay. So this is a fantastic protocol, and I'm not going to spend a lot of time on it, but I like it for many reasons, and many others in the field do. The reason being, it's a kind of a simple protocol, and it does actually work pretty well, and it really doesn't need any identities, and it doesn't restrict the number of people connected to the network, and so on and so forth. Yeah. Okay. Okay. Miners nodes solve POC puzzles to earn BTC reward as well. Yes, they do. Now, let me clarify this question about BTC reward. Think of it this way: you could set up this whole system in a computer science way without any rewards. Okay, you could just follow the previous protocol and not distribute any rewards at all. Okay, if you want to distribute rewards, yes, surely you can put a virtual currency and pay the block founder some money for getting lucky on that round. Okay, you can do this. But that kind of stuff is more to do with incentives for people to participate than to do with the correctness of the protocol itself. Okay, so for a few minutes, if you like, just forget about block rewards and so on and so forth. Imagine that there's some incentive for people to connect and do this anyway. Okay, if they were willing to do this, actually, there's nothing preventing you from running this for any replicated computation. It doesn't even need to have a currency built in. Okay, and that's kind of the cool thing, right? Because you can run pretty much anything around this. You may want to build a currency network, you may not want to build a currency network, and block rewards have nothing to do with the correctness of the protocol. Okay, so I hope this part is a bit clear. Yeah, how is it possible to attract voluntary nodes? Well, that's a question that that there are a lot of things people do in real life which don't involve money, and yeah, you use one of those mechanisms perhaps. Okay, like building open source communities, for example. Even prior to Bitcoin, that has happened. Lots of open source systems like Unix and so on and so forth have had voluntary contributions as well, without there being the presence of a currency network. Yeah. So leaving sort of the incentive story out, the correctness of the protocol is actually fairly interesting in its own right, is what I'm trying to point out. Yeah. So this is fantastic because you have a simple protocol that people can actually work with. They understand how it works. They can implement it. Most computer science students would be able to implement Bitcoin's protocol in a semester-long project for sure. Okay, and certainly the simple versions of it. Okay. The problem with this protocol is that it has very poor throughputs. Okay, so for example, Bitcoin, and by the way, this particular Nakamoto consensus protocol has been used with reparameterizations again and again and again in lots of cryptocurrencies, including Ethereum and so on and so forth, right? So what happens is that you can change, for example, the amount of delay between two blocks. Instead of having 10 minutes, you can do 2 minutes, you can do 3 minutes, you can do 1 minute, you can do 15 seconds if you like. Okay, there's a limit to that. But you can actually reduce the time window in your deployment of the protocol, right? So Ethereum, for example, has 12 to 15 seconds supposedly as the desired interval between blocks, whereas Bitcoin does 10 minutes. And what happens is that effectively, if you think about it, the problem is this protocol itself fundamentally does not allow you to scale throughput. What throughput is the number of transactions per unit time on average. Okay, so and specifically, if you look at the protocol's design, you can basically transmit about 2 to 4 kilobytes per second. Okay, of Nakamoto consensus allows you to do about 2 to 4 kilobytes per second on even a network that has, let's say, a few tens of megabytes worth of real bandwidth, right? If you look at the real network bandwidth available for broadcasting messages, actually the protocol will only allow you to use about 2 to 4 kilobytes worth of it. Okay, and that translates to, if you look at the size of every block and the signature mechanisms and so on, it translates to about 12 transactions per second. Okay, now I'm not saying that you have to be tied to 12. good engineering can get you, let's say, a factor of 5 or factor of 10 more than this, but it's not going to give you, for example, usage of the full megabytes worth of bandwidth that's available. Okay, so that's a known sort of fact in the academic literature, and so on and so forth. Okay, right. Okay, but actually, the point that I was trying to reflect on the previous slide, which I should complete, is that centralized payments providers, right? They actually have demand for processing tens of thousands of transactions per second. Okay, not few transactions per second. They often do process 3,000, 5,000, 10,000 transactions a second on a regular basis, right? So if you really want this kind of technology to, for example, offer an alternative to payment systems, centralized payment systems, one of the sort of interesting goals is how to achieve that kind of throughput. Okay. There's another sort of issue that gets talked about in computer systems and especially in the blockchain community, is to do with decentralization, right? And so really, what is decentralization? Let's think about it, okay, for 1 minute. So the way you want to think about this, at least from the way that I like to think about this, is that you can't really control what's going to be the distribution of computational power that some entity will own in the network. Okay, if let's say a country decides to invest a lot in the mining infrastructure of Bitcoin.
Singapore law are very strict, but sometimes I think things go wrong, they start amending. Before that, blur. So are they supposed to run on the road and also pedestrian at the same time? Well, now they chung the crossing like that one, you know, don't even tell as if the pedestrian. But are they?
Sorry, is that a question?
I go in and park. Can you see?
You can technically go inside and park at there.
Yeah, I'm going to. I'm always park there.
Okay, looks like there was somebody's mic had turned off accidentally. It's turned on accidentally. Okay, continuing to what I was saying is that this idea of decentralization is saying, look, we can't really control how much people will connect into a permissionless network. Okay, we can't. I mean, it's permissionless, so anybody can connect as much as they want. And if you think about wealth distribution in the world, it follows this exponential curve where there are a lot of wealth is concentrated in a few hands. Okay, and then it sort of tapers off, and most of the people don't have a lot of wealth. And that's the same sort of concentration curves that we have seen in terms of mining power on most of these large-scale blockchains, right? There are some miners that own a lot of computation power, and others that don't own all that much. Okay, so given that you can't really control who connects to the network, it's difficult to say that a certain set of nodes are owned by some entity or not. Okay, what you can do, however, is the following. What you can do is, if you allow a lot of people, a lot of nodes to be able to commit transactions per minute, for example, right? If you want to allow people to do lots of blocks per unit time, then you're somewhat more decentralized. And the reason is, you think of it this way, every block is like taking a sample from this computational power mechanism, right? So basically, some node on the network is being asked to propose a block. Okay, if you do one block in 10 minutes, then basically somebody gets lucky for that 10 minutes, and a very few people get lucky in an hour. Only six computers get lucky in an hour. Okay, whereas if you do, let's say, 600 blocks in an hour, okay, then lots and lots of people are able to push at least one block per hour. Okay, so what you will do is, if you sample a lot per unit time, you will be able to touch these little tails in the distribution, these small miners and people with laptops and so on. You would be able to allow them to push transactions of their choosing, of their choice, if simply you had a lot more blocks per unit time. Okay, You can't control the underlying distribution, right? That's a difficult problem to control. Okay, but what you can control is you can design protocols which allow lots of blocks per unit times to be chosen randomly from whoever is on the network. Okay, so that's how I like to think about decentralization. These protocols should strive to push as many possible small blocks as possible, subject to the amount of bandwidth that's totally available, right? So if you have limited amount of bandwidth, finally you will saturate that bandwidth. But if you can, try to push as many small blocks as possible so that as many little miners as possible have the option to propose transactions of their choice. Okay, so that's my notion of decentralization. I'm not going to argue about which particular entities on which particular network should or should not have invested their computational power to begin with, because that's something that we can't really control anyway. Okay, and one of the issues is that Nakamura consensus, okay, it has this sort of curve which has been sort of proven both mathematically now and also through experimental data as well, right? People kind of know that your block delay, the way you set that up, has some sort of, shall we say, if you think about there being sort of, Bitcoin says that there have to be 50% miners have to be honest, at least 50%, right? So let's treat that for 2 minutes as the optimal answer that you could best hope to get. Okay. So if you think about how this plays out, is that if you set your block interval to be, let's say, a lot bigger than the total time it takes for a block to excuse me, for a block to propagate on the network, right? Let's say you set the interblock generation time to be 60 times the time taken to propagate the block on the network. Let's say it takes 2 seconds to propagate, and you set 120 seconds as the interblock generation time. Then basically you're going to be operating very close to the optimal security resilience, right? You'll be able to tolerate something like close to like 45% of the adversary. Okay, I'm not being precise here, but I just want to point out that the protocol has these characteristics. The Bitcoin Nakamoto consensus protocol is that you can parameterize it and you can run it in different sort of, time intervals, as I mentioned, 10 minutes to 2 minutes and so on and so forth. And the lower you get, the closer you get to the actual propagation time of the block, the lower is the security tolerated by this system. Okay, so that's really kind of an interesting thing, and the nice takeaway is that if you keep it 3 times the block propagation time, so let's say you have a 1 megabyte block and it takes 3 seconds to propagate on Bitcoin's network or Ethereum's network, right? Set your interblock generation time to 3 times that, you're going to tolerate a pretty high level of adversaries in the system, definitely more than 30%. So this has been sort of shown. Okay. So the blockchain trilemma tells us that blah blah blah, increase scalability, Okay, look, I first of all, the blockchain trilemma is not a trilemma in academic literature. Okay, it's not at all a proven fact. Okay, so I'm going to treat that with a lot of suspicion in this talk. Okay, in fact, what you will see is that you can break the trilemma. I mean, the trilemma is supposed to say you can't do X, Y, and Z, and actually you can. Okay, so I'd request you to think about this in a scientific way and put aside all that you've heard from the sort of the empirical messages around this. Focus on the essence of this, and hopefully you'll believe what I'm saying. Okay, there is no trilemma as such. Yeah. Okay. Moving forward, okay, and I'm not, by the way, I'm not suggesting anything about Solana or Polygon or Zilliqa or anything, right? I mean, I'm just trying to sort of present to you the scientific facts as I know from the academic literature. It doesn't say anything about what can or can't be happening in the real network. Yeah. Right. So the interesting point is that if you do this badly, if you design the protocol badly and you try to make it very fast, and you just simply do that by setting the interblock arrival time to be very, very small, you're basically going to have a very unsafe system. Because if you think about it, lots of people will simultaneously be mining blocks, and those blocks will not have reached other people. So they're going to be like halfway through the transition. So one miner in the middle might get here this block, and another miner close to the middle might get the other block. So they will accept different blocks, and you'll get these very large scale sort of confusion in the network, where some of the people are accepting, let's say, the black blocks, and some of the other miners are accepting the blue block, and so on and so forth. Okay, you get this little sort of disagreed network, if you will, right? And they'll take a very long time to converge on which blocks are actually confirmed. Okay, and you do it really badly, you can have adversarial games here, where some miners are playing games and they're sort of getting you to disagree by design. Okay, so that's really the interesting thing about this protocol. Okay, so the question we've been trying to sort of solve in the research community is, can we do better than what Nakamoto consensus does, or its reparameterizations will do? Okay, and the answer is you can. And there are some sort of classical algorithms that you could start to think about to solve this problem. One of these algorithms is actually called the Byzantine agreement protocol. Okay, actually there are two of these which are kind of closely related. There's Byzantine consensus, and there's Byzantine agreement. Byzantine agreement and Byzantine broadcast. Okay, so they're kind of related. In this talk, let me focus on Byzantine agreement protocol. Okay, this is a classical protocol known for almost like 30 to 40 years. Okay, and this is what it does. Okay, if you have, let's say, n parties, n computers, okay, and let's say some fraction out of those n, let's say f out of those n are malicious, we call them Byzantine. Okay, then getting them to agree on the same value, okay, is possible. Okay, and the way you do this is you pretty much run this Byzantine consensus or Byzantine agreement protocol. Okay, and by the way, this problem was first described in a kind of a cute way by saying, hey, look, think of this as an army of generals who have surrounded a city, and they need to decide whether at dawn they'll attack the city or they will retreat. And each of these generals gets to make a decision and send a message to the other generals saying, let's attack or let's retreat. Okay, and you can imagine there being some sort of a commander who's basically helping coordinate things, but basically the network is unreliable. That means messages are being sent back and forth using pigeons or messengers and whatnot, and there is no one global place where everybody can see the outcome. Okay, so what happens is, if all of them agree to attack the city at dawn, they will win the battle. If all of them decide to retreat, then no lives are lost and things can go back to normal. But if half of them attack and half of them don't, or some of them attack and some of them don't, then basically they will lose the war and some generals will die as part of the process. Okay, so you don't want this kind of uncoordinated attack. Okay, so this is the problem, right? There are n generals. They won't need to agree on retreat or attack, and the message protocol can only be sent via messages, peer-to-peer messages. That means one guy can send a message to the other guy, and so on and so forth, right? And it turns out that there are protocols that solve this. Okay, this is a very well-known computer science problem, and there's some interesting solutions to this. Okay, so the question is, if this protocol exists even before blockchains did, why can't I just use this protocol to solve blockchains? Okay, so here's the thing. You can say, yes, of course we can use it, right? Just run this protocol once for every block. Okay, once in every 10 minutes, you just run this protocol between all those n nodes on the infrastructure, and the algorithm is written down. They just have to run it. Okay, and they will agree on one block at 10 o'clock, one block on 11 o'clock, and one block at 10 minutes after 10, one block at 20 minutes after 10, and so on and so forth. Okay, so in principle, yeah, you can do it. Okay, in fact, you can. Now, there is a catch, however. Okay, the catch is this protocol, and some of you may have noticed this. So the protocol says that there are n and exactly n such parties playing the protocol. Okay, there are n computers connected. Okay, n can be 20, 30, 40. but or 500 or a billion, doesn't matter. But the point is the protocol needs to know exactly the number of nodes on the infrastructure. Okay, it needs to know how many computers are playing this game. That's one of the big problems. In a blockchain network, which is permissionless, we don't know how many computers are connected. So we don't know what n is. And so if we want to use this protocol, this classical protocol, which would have solved our problem, we would first need to agree how many computers are on the network. So you need to know what n is, set that value in your code, and then you can run this protocol. Okay? That's the issue with it. Okay, and this is why this classical idea, the classical problem, does not solve what we need for a permissionless blockchain. Okay? So this led us to sort of think about how we might be able to solve this problem, okay, using a technique called as blockchain sharding. Okay, and I'm just introducing this concept the way it's described in the original paper at ACM CCS, and of course different versions of this have come about during implementations of large-scale systems. Okay, but let me give you the basic idea. So the idea is you take all of these nodes, okay, and what you do is you ask them to solve a proof of work puzzle in that time instance. Okay, let's say the first 10 minutes of this protocol. Okay, and you'll repeat this game in every epoch. What you do is you basically divide this network into sub-networks that produce the same puzzle result, the same solution for the proof of work puzzle. Okay, so imagine your proof of work puzzle can produce, let's say, 3 different valid answers. So all of those which produce the same valid answer will be grouped in the same shard or the same sub-network, if you will. And so basically there are 3 sub-networks, and these sub-networks will get created once every epoch. So one new shard for each block, for example. Okay, interestingly, once you have been able to divide a large network into these sub-networks just by solving a proof of work, again, there's a way to do that, then you can have a little sort of quick round where all of these nodes in the first shard tell each other that, hey, I'm present in this shard, I'm present in this shard, I'm present in this shard, and so on and so forth. Okay, so they'll be able to advertise their solutions, and therefore they will know who are the other people in their shard. So they know n, they know how many other people there are in this network. Okay, and then they just run, as I mentioned, the classical Byzantine agreement protocol that allows them to mine a block. Okay, the cool thing about this idea is that if you have more nodes on the network, then you can just create more shards. So in effect, what's happening here is that per instance, like in the same 10 minutes or the same minute, if you will, if there are, let's say 10 shards or 6 shards, you can create 6 blocks in parallel. Okay, so the entire network is kind of automatically parallelized, and each subnetwork is agreeing on one block as we speak. Okay, so this is the idea or concept of sharding. Okay, and in fact, the more the computation power that you connect, the more shards you can create, and more blocks can be created per unit time. So you're kind of increasing the throughput as you're creating more and more shards. Okay, and there's a way to do this securely. Okay, and the idea is that you look at the same sort of puzzle that you use in Bitcoin. You kind of use the same thing. You just look at a few digits after the leading zeros, and that gives you an ID, a shard ID, and that allows you to automatically partition puzzles solutions into these shards. Okay, that's the main idea. Okay. And then of course the way to think about this in one shard, right, basically you've got some honest nodes, okay, and you'll have some dishonest nodes. Okay, because think of this as this is one shard, and the idea of putting a node in that shard, okay, as a result of solving this random puzzle is like throwing a ball in a bin, Okay, the blue ball is honest miners, red balls are malicious miners, and you want to just make sure that whatever happens, the ratio of the honest miners corresponding to the ratio of divided by the number of dishonest miners, that ratio should remain 3:1, at least 3:1. You need that in order to be able to get the guarantees from Byzantine agreement. Okay, so if this condition is true, you should be able to run a classical Byzantine agreement protocol and solve your problem. Okay, so this is how basically sharding-based systems, the network sharding-based systems work. Okay, and so how much, I won't do the calculations for you, but basically if you want to tolerate 20% adversaries in the entire network, you should choose roughly 600 members per shard. If you're doing fourth, it should be 1800 and so on and so forth. Okay. Right, so there are some more assumptions, and in the interest of time, I will not talk about them. And really the paper does actually go and engineer a bit more beyond this basic concept in order to make this thing scale. Okay, but here is what I want you to take a look at. Okay, so before this work, basically the state of the art is shown in black. Okay, the amount of adversaries that could be tolerated on these layer 1 permissionless blockchains was roughly 20%. I mean, it was actually, the protocols were doing a third. Some of them were doing less than 50%, and 20% was also normal, but they had different level of throughput and decentralization. Okay, so the sharding idea actually gets you to about 1/3, okay, in concept, and gets you high throughput and fairly good latencies. Okay, so about 30-second latencies is something that the paper sort of, was aspiring to get to. Okay, and we had some intuition that we would get to about 30 seconds latency at that time. Okay, and decentralization is okay. There are about 1 to 3 proposals per second, which is a lot better than Bitcoin. Okay, this is several, 1,000 times better, much more compared to what Bitcoin does. Okay, so it's definitely better than that. But resilience was still not close to half. Okay, which is what Nakamoto consensus can do for you. Okay. And so what we did after that is we started to work on a solution that would basically improve on that dimension by improving throughput in a much better way. And what we started to look at is, can you actually take Bitcoin's Nakamoto protocol itself, okay, and really get it to start to scale up? How would you get that protocol to start to scale up? Okay, what really could be done using that well-established protocol? Okay, and so some interesting results came out. Okay, so the first thing to remember is that, see, we've already established that Nakamoto consensus, if you choose the block interval, and that means that the time of creating, the time distance between creating 2 blocks using Nakamoto or Bitcoin's protocol, if it's anything more than, let's say, 3 to 5 times the time taken to propagate that block on the network, okay, you're already getting pretty good resilience from the protocol. Okay? Definitely more than 30% and so on and so forth. Okay, so it's actually provably safe, which is a fantastic thing to have. Okay, and this includes all possible attacks. Okay, so you can think about attacks where the adversary is creating, not following the rules of the game. That means they're creating blocks that are not from the last block that they know, or they're basically extending from blocks that are not on the longest chain in their local copy. You can think about all of these other ideas. Okay, you're free to do whatever you want, okay, as an adversary. This protocol would still be safe. Okay, it says something about being safe under all other strategies of the attacker. Okay, so these all attack attempts will become invalid. Okay, and so one of the nice things we started to look at is, why don't we use this particular protocol in our construction and try to get more throughput. So this is what we noticed. Okay, we noticed that the propagation delay for a block, okay, is a function, of course, it's a function of the size of the block. If you use a 20 kilobyte block, which is a small block, okay, you will notice these kind of characteristics. You will be able to send one single block on the network, but at the same time, you can also start to flood lots of 20 kilobyte blocks at the same time, and they'll all get delivered roughly at the same time. Okay, so you can parallelly broadcast lots of blocks, small blocks on the network. Okay, and what this does is this is nice because if I choose small block sizes, and if I could invent an algorithm that just sends, let's say, hundreds of 20 kilobyte blocks, okay, then it's really, really useful because first of all, within the same unit of time, you've got 100 times more blocks being mined. Okay, that means your throughput actually just goes much, much better. Secondly, you see lots of different miners are able to push their blocks. And that's the whole point of decentralization. Getting lots of people to be able to choose transactions and get them accepted is really what, in my view, decentralization is about, right? And really, I mean, finding these sort of connections between these parameters was very, very helpful for us. Okay, so I won't get into the full details of exactly how these things relate or what the protocol construction is. The paper that I'm listing at the bottom here is the one that describes the whole architecture. And really, what it does is simply it will run up to k chains, okay, or any number of chains as you want. Okay, each one of these chain you can think of it as a Nakamoto consensus protocol. Okay, and the protocol is basically what it's doing is you're using one proof of work and putting solutions based on whatever is the result of the proof of work. You will either push it to chain 1 or chain 2 or chain 0 or chain 99, or you just keep adding blocks to one of these chains per round. Okay, so that's what you do. Okay, so I won't get into the details of this, but the point here is that instead of running one instance of the Bitcoin protocol, if you ran 1,000 instances of the Bitcoin protocol on a miner simultaneously, you would be able to actually mine a lot more blocks per unit time. Okay, the trick is not to do separate proof of work for each one of them. It's to do the same proof of work and look at the result of the proof of work and map it to one of these chains. Okay, so if let's say you could look at a few bits in the output string and say, okay, if the string is 00000, it goes to chain 0. If it's 00001, you push it to chain 1, and so on and so forth. Okay, so there is a particular construction that I'm not describing in full detail here, which allows you to achieve, just using Nakamoto consensus, pretty high scalability. Okay, so it's a simple protocol. It comes with a proof, much like the Bitcoin protocol, and it achieves pretty interesting scalability properties. Okay, now there is a question about, well, you've got 1,000 chains instead of one on every miner running. So how do you order the blocks across all of these chains? Okay, when I finally print out the sequence of blocks that I've accepted as a miner, what order will I use? Okay, so the naive thinking might suggest that, hey, you should do basically, so first of all, you should use Nakamoto consensus. So you only take the longest chain, okay, as Nakamoto consensus says. And then one naive idea would be to just string them as take the 0th block, the first block of the chain number 0, take the first block of chain number 1, and so on. Take all the first blocks, then take all the second blocks, then take all the third blocks. And that's a sequence that you could print out. Okay, so it turns out that this is not the best thing to do. Okay, if you really want this to work very, very well, it does give you a full ordering, but the latency that you're going to get is going to be, it's not going to be great. Okay, and the reason is that there are going to be some chains that are very slow and some chains that are very fast. Some have a lot more blocks than the others. Okay, because this is a probabilistic process, and so it's not going to sort of work very well because you'll get stuck on the chains that are running the slowest. Okay, so it turns out this is not a great idea, and there's actually an alternative scheme that I will not talk about. There's a little trickery you can do with keeping virtual lengths. and you can get away by ordering them in a slightly different way. But the end result is the same. You end up getting a lot more blocks per unit time. They're all confirmed, they're fully ordered, and the throughput happens to be much, much higher. So to give you an example here, you can do tens of, thousands of transactions per second, okay, as opposed to doing a few tens of transactions with the original Bitcoin system, simply because you're running many instances of this protocol, by the way, right? So you get very high transaction rates and throughputs, close to whatever bandwidth is available. So the more bandwidth you have on your mining network, the more throughput you can get. I think I'll for the interest of time, I'll start to sort of wind this down. Okay. Just very briefly, let me bring you to the final learnings we've had with this, which is that you can actually get pretty high decentralization and much better latencies as well using this particular protocol. And so this is sort of where I think the state of the art kind of sort of roughly in this region is where the state of the art is. I'd just like to mention that we've also started to show that you can tolerate more than 50% adversaries. So you may have heard of these 51% attacks on Bitcoin. Actually, turns out you can design protocols that will tolerate more than 51% adversaries as well. And so that's something that's just happened fairly recently. The paper is available on my website. You can also go and see it soon on the IEEE Security and Privacy conference webpage. So here are the takeaways. Okay, I think decentralized systems like blockchains offer very good algorithmic problems to look at. It's an exciting space. I think scalability is a particularly interesting problem to look into for layer 1 blockchains. Simplicity is something that we should keep in mind going forward when we are designing these protocols. And I think there is still room to improve some of these constants. Some of the better engineering can reduce some of the parameters a little bit better. And that's something that's definitely worth looking at. Lastly, there are lots of connections that I have not talked about in this talk, but they're worth looking into, which is thinking about blockchains as a database and looking at the properties of a database and that of a blockchain, thinking about proof of stake versus proof of work. There are a whole set of issues to think about, fairness and incentive mechanisms and so on and so forth. And lastly, people are also looking at off-chain solutions to scale up blockchains, and how these two, the layer 1 and the layer 2 and the off-chain work together is very interesting grounds for further research. Okay. So with that, I'll just like to thank all of my collaborators whose works I've combined and put here. And with that, if you'd like to take any questions, we can stop at this point. Right. Are there any questions? Hopefully I've answered one of Sebastian's questions, that the scalability trilemma is really not quite there. You can actually design systems that try to achieve the best of whatever is the best you can get from the bandwidth available on the network. Okay, there's another related question. I wanted to check with the hosts. Is it okay to answer this question, or should we close for the day?
Yeah, maybe we can call it for the day. Thank you so much for the insightful session, Prof. Pratik. Thank you.
Thank you so much. Thanks a lot. Bye-bye.
Bye. And thank you everyone for joining. Have a good day.